In the first half of chapter 3, we're basically going to be dealing with like shortcuts on how to take derivatives. Because by the end of chapter 2, when we started using the definition of a derivative to take the derivative things, we saw that even for relatively simple functions, this was getting like really onerous and oftentimes like algebraically absurdly tricky. So most of what the first half of the chapter 3 is devoted to is like shortcuts around this, and we'll take things that would be like maybe a whole sheet of algebra manipulations in your using the definition to something to do with mental math. That's right. All right. So we're going to start with just a series of theorems. These theorems are all just like derivative shortcuts. So the first one is the derivative of a constant is 0, right? Let's prove that. If we're going to try to prove a derivative rule, what are we going to end up having to use? The definition of the derivative. Very good. Oh, say f of x is c. So what is f of x plus h when f of x is equal to c? What do I get when I plug x plus h in? Just get c, right? Doesn't matter what x is, just f of anything, it's just c, right? Oops, forgot my limit. So c minus c is 0. 0 over h is 0. And the limit of a constant is the constant. Important that you're hanging on to that limit sign all the way to the end, right? Because if you try doing direct substitution too early, you get something that's indeterminate. But that's the proof. Oh, that's not so bad, Mr. Kulik. Well, that's a pretty easy. It's one you probably could have looked at. All right. Next theorem. The derivative of x is what's the slope of y equals x? There you go. That's the derivative. So do the same thing. We'll prove this. We're not going to prove all these things, but some of these that are pretty simple to do, we'll go ahead and prove these that aren't like an incredible headache, just so you can get an idea of like how to do some of these things. Would Mr. Kulik ask you to prove things like this on the test? Probably not. But you know, it's good to see how this stuff is done. Right? I imagine that a few of us in here will be engineering or mathematics students, and in your Calc 1, 2, 3 courses, you'll have to do stuff like this on occasion. So it's good to at least have had seen some of it, even if you're not, I'm not going to require you guys to do a bunch of it. Okay. So those guys are like pretty narrow, right? Those have limited usefulness. The one that you guys have been waiting for is this one. This is your power property for a derivative. I'm going to skip the proof for this because it involves really, I can't prove it generally, but this is true for any n. the proof that I would do would just be for like positive whole number ends, and I would use the binomial formula or the binomial expansion to do it, but it's kind of tedious and it's not really that informative. So I'm just going to skip it. Let's take a little time out here now that we've gotten that power rule out and just do some practice using that. So if I have f of x equals x to the sixth, what's the derivative of that going to be? To the fifth. Everybody's okay with that? So the power rule, the exponent becomes the coefficient, and then you subtract 1 from the exponent. What about y equals x to the 1,000? 1,000x to the 999. Cool. Look at all this nice mental math problems here we have. Let's say we have z equals 2 to the fifth. Yeah. Who almost started trying to do the power rule to that? There's no variable. That's a constant. Oh, Mr. Kulik, you're so sneaky. Yeah, I try. How about f of x is equal to 1 over x? So you'd want to think about this as x to the negative 1. So that would become negative x to the negative 2, or negative 1 over x squared. This kind of stuff here is like the foundation of first-year calculus, is being able to do these kind of algebraic manipulations so that the calculus becomes easy. This is a trick that we're going to have, or these kinds of tricks we're going to see over and over and over again. Mr. Gulick's going to pull out all kinds of Algebra 2 rules that you're going to be like, oh my, really? And like take something that you spent like a half a sheet of paper doing and do it in like 2 steps by like rewriting it in a clever way to avoid having to do complicated calculus by doing some sneaky algebra. But these kind of tricks we're going to see over and over and over again. And getting good at calculus really means like finding ways not to have to do the calculus by being sneaky at algebra. I know. It's like, what? It's like, yep, I'm telling you. Avoid doing the subject that we're actually supposed to be doing. All right. Y equals cube root of x. Yeah, so you want to think about that as x to the 1/3. And then that could have 1/3 x to the negative 2/3. Or you could write that as 1 over 3 cube roots of x squared. You guys feel okay doing these, Paul? Shh. Yeah, you can walk even. Like it's no rush, unless it's a rush for you. Yeah. Oh, okay.
I missed like 1 minute.
I thought you were making like a poop your pants insinuation there. No. Okay. All right. But we feel okay about doing this, right? And I want to point out to you, like, this is almost identical to something you had on the test. And this was like a real colossal pain in the butt to do the derivative with the definition. And that was something that was a mental math problem for us. which is such a massive improvement and time saver. You know what I mean? That's what I'm talking about, Mr. Kulik. Get me all the shortcuts. All right, I'm going to define a new term here. So we say the normal line to a curve C. Oops. I just need to write. I can't talk and write at the same time today. Okay, so the normal line to a curve is at point P is the line that goes through point P. It's also perpendicular to the tangent at P. So let's say that this is our curve C. And let's say that this is our point here. So our tangent might look something like that. Got away from me a little bit. Everybody's okay there? So there's a tangent through P. Our normal then is going to look like that. Everybody's cool visually what we're talking about? Does anybody remember way back to like Algebra 1, the relationship between perpendicular lines and their slopes? Negative reciprocals. Very good. Yep. So let's look at an example now where we'll actually we'll calculate or find the normal line for something rather than just Mr. Kulik drawing a messy looking sketch. Let's say we want to find the normal line to the curve y equals x times square root x at the point 1, 1. So if we want to write the equation for a line, we need two things, right? We need a slope and a point. Everybody's cool with that? The point we're given in the problem. We know that that normal has to pass through 1, 1. And the slope we know is going to be the negative reciprocal for the slope of the tangent line when x is equal to 1. So that's just some like fancy math notation. Everybody's okay with that? So again, dy dx is our symbol for the derivative. The vertical bar just means that we're going to evaluate, and then the subscript tells you where we're evaluating at. The AP loves this notation. You'll see it oftentimes when looking at problems. So I'm going to try to use it quite frequently. It's also a very common mathematics notation, but the AP seems to really like this notation. It's very compact, which is nice for typing. Okay, so I guess the first order of business is to find dy dx, right? With the way my curve is currently written, can I take the derivative of it? No, right? So I'm going to have to rewrite this. So the square root of x is the same as x to the 1/2. So x times x to the 1/2 is x to the 3/2. How did I get that? Added fractions. Everybody's cool? When we multiply two things together, we add their exponents when they have like bases. Now we can take the derivative, and that gives me 3 over 2 x to the 1/2. And then I know the slope of the tangent line at x equals 1 is just going to be me plugging 1 into that derivative. So I get 3 over 2. Everybody's cool with that? So the slope for my normal line would be the negative reciprocal of that, so negative 2/3. And now I can just do my point slope equation for a line. Y minus y1 equals m times x minus x1. Distribute through the negative 2/3 and then add over the 1. And here's my equation for my normie. What do you guys think? It's all right. Jillian?
Can you explain the portion under the word normal to the left? Like we did when we subtracted one.
Oh, this is the point slope equation for a line.
Oh, no, I'm sorry. Like under the where you have n 11 minus 1.
Oh, that's equals. That's just an equal sign.
Oh.
That's equals 1, negative 1 over the derivative evaluated at 1. Yeah, no, 11 minus 1 makes no sense there, right? Yeah, for sure.
I'm good.
Okay. That's an excellent question, right? Like, clears up everything. It's like, that wasn't an 11. It looks like an 11. I don't often write a vertical equal sign like that, so totally understandable being confused. Maybe we'll just do like that, right? We'll do that. That takes care of it, right?
Yes, that is.
Yeah, no problem. That's funny. I'm gonna giggle about that again later. Not at your expense, but like
I will also
it's funny though. If you can't laugh at yourself on stuff like that, like, come on. All right, back to some more shortcuts. So assuming that c is some constant, and we have f that's differentiable, we can say the following. The derivative of c times a function f of x is going to be c times the derivative of the function f of x. What's that really saying? We can just ignore the constants, right? We can just ignore the constants, do the derivative, put the constant, multiply the constant back on when you're done. Let's just prove that real quick. This is a relatively easy one to do. Oh, let's make that, I guess. Well, I want to use a different one. No, that's. Ugh, come on, Mr. Gulick. Forget your limit. Know your limits. Ha 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 ha. Or not, you know. I notice that I have a greatest common factor of c in the numerator. Everybody see that? And since that c doesn't involve the argument of our limit, there's no h involved with that c, I can take that c and pull it all the way outside the limit. And this part that's left is just by definition f prime of x. Is everybody cool with that? Okay. Our next one, well, I guess I want to add g here too. So the derivative of f of x plus g of x is just the derivative of f of x plus the derivative of g of x. And works the same way for subtraction. What are we really saying here? We can just distribute our derivative to all the terms in our function, right? Okay. I'm going to not bother to prove this one. And let's just go to some examples. So let's say we have the function y equals x to the 8th plus 12x to the 5th minus 4x to the 4th plus 10x to the 3rd minus 6x plus 5. If I were to take the derivative of this using the definition of a derivative, what a nightmare. That's like a full sheet of paper of scribbles. I'm turning that sucker landscape style, and it's still wrapping onto more than one line to do the expansions there. No thank you, sir. Now, with what we know, I'm going to write out what I'm doing in my head. So everybody can, if you're going back and looking at your notes, you can see what's going on. But this should be something we can do in our head, but I'm going to write out the steps that I'm doing internally, just so everybody's clear as to what I'm doing. So if I take the derivative of both sides, the previous two properties allow me to distribute that derivative to each term in my polynomial, and the theorem prior to that allows me to pull the coefficients outside of the derivatives. Now, if you feel comfortable just doing this like all internally with mental math, that is okay at this stage. But I'm going to, just for the purposes of this example being in the notes, really kind of show how I'm using those properties or those derivative theorems. Everybody's cool how I've taken the derivative of one big thing and wrote it as like 6 little derivatives? Okay, so now it's just derivative time. So I'll go ahead and I'll do my derivatives. And then I'll just do some simplifying to combine some like terms or multiply some stuff out. And I would hazard to guess if we tried using the definition, I'm not even sure I would have been able to write out the expansion of x plus h to the 8th yet. And we're already done. I think I'd still be writing out that expansion. What a lifesaver this is. Holy simoleons. That's an improvement. What do you guys think? And again, if that's a mental math problem to you, even at this stage of the game, great. If it's not yet a mental math problem to you, try to make it. We'll do enough practice in the first section's homework. Hopefully by the end of the first section's homework, that is a mental math problem for you. And going forward, the sooner that these derivative problems can kind of become mental maths, the better, because there becomes a lot of layers to some of these problems later. And if you're able to do stuff like this, without having to write down a lot of extra work, it just becomes a little less cluttered moving forward. Now, I will probably still continue to do this in the notes, at least at the first time through some of the more complicated examples, just to kind of illustrate what's going on. And if you ever need me to be like, hey, can you do what are you doing in your head when you did that? I'm happy to go out and write that stuff down if I don't. But at least the first time through, I'll make sure to try to do something like this. Okay? But not every time. All right. Okay. Let's say we ask you to find the points where f prime of x is equal to 0, given that f of x is x to the 4th minus 6x squared plus 4. First order of business would be to find f prime, which would be
4x minus 12x.
Everybody feel good on how Teagues did that? Perfectly reasonable for that to be a mental math problem. There's no work you need to show for that. Okay, so to solve this now, when it's equal to 0, what would I want to do to solve this equation?
First plot x.
Okay, in fact, let's take out a 4x. X would have been enough, but as long as we're factoring things out, let's do the whole GCF. Okay, now what? Great. I can apply the zero product property to set each factor equal to 0, and then solve each one independently. So I divide both sides by 4 to get x equals 0. I add 3 to both sides, and then square root both sides to get plus or minus root 3. Am I done? Why not? Yeah, we need to find the y's as well. Where are we going to plug these x's in to get the y's? I have to plug them into f. Yeah. What are these points where the derivative is 0? What are those going to be representing? Places where the tangent is a horizontal line. Great. Or they could be potential extrema. Maxes and mins, potentially. Paul?
Why did you plug in the points to just f of x now?
Well, if I plug them into the derivative, what am I going to get? 0, because that's what I solved them equal to. But it's asking for the points where the derivative is 0.
Oh.
So it wants the points from f where that have 0 slopes.
Got it.
You know what I mean?
Yeah.
So let's see. Here I get 4 So that's the 0.04. See, when I plug that in, I'm going to get 9 minus 6 times 3 plus 4. So that's negative 5. So that's negative root 3 comma negative 5. I plug the positive in. Since all the exponents are even anyways, I'll get the exact same thing. So those are my answers. Since this is a polynomial, I also know that it's continuous and smooth, like there's no corners or anything kooky going on. So these are the extrema. I don't know which one is a maximum or minimum, right? I don't know what kind of extrema they are, but I know that's the extrema. Everybody's cool? That's pretty neat. Okay, Blake. Certainly. Up until this point, everything we've done has been with polynomials, right? Let's talk some about exponential functions. So let's say that we suppose that f of x is equal to a, and we want to find the derivative. I'm sorry, f of x is equal to a to the x. What are you talking about, Mr. Cooley? How do I know that's an exponential function? Just by looking at it? The x is in the variable. Or the x is in the variable. The variable's in the exponent. Mr. Cooley, you're funny today. Yeah. Hilarious. So, again, if I don't have a shortcut, we'll go ahead and use our definition. Now, what can I do with this? Does anybody see a greatest common factor? Let's rewrite it a different way. Maybe it'll be a little bit more obvious. A to the x plus h is the same thing as a to the x times a to the h. Everybody agree with that? Now do you see a greatest common factor? Sure, Mr. Kulik. A to the x. And if you look at that, you see that factor of a to the x. That factor of a to the x doesn't contain any h's. So I can just pull that outside of my limit. Everybody doing okay so far? Now, do you recognize that limit that we're left with? That's something. Here, let me write it a different way. Maybe it'll become more recognizable. H is the same thing as h plus 0, right? 1 is the same thing as a to the 0, right? What about that? Does that look familiar? That's a definition. What is that? It's not e. It's the derivative of our function at 0. Right? This is just f of like 0 plus h, and this is minus f of 0. Now you see it? Oh, Mr. Kulik, that's a deep pull. Just the definition of the derivative at a point. All right, so what's now we are making one assumption here when we wrote this. What are we assuming? Yes, that f is differentiable at 0, right? Let's try a numeric example just to kind of see what's going on here. Well, that got long, didn't it? Let's say f of x is equal to 2 to the x. Well, the derivative of this should just be 2 to the x times f prime of 0, based on what we just did earlier. And f prime of 0 is the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h, which in our case, or with this specific f of x, is 2 to the h minus 1 over h. Now notice that I can't evaluate that limit using direct substitution, right? What else could I do, though? What other ways can I evaluate a limit if I can't use direct substitution?
Usually just other limit laws to
You could try. Yeah, why don't we use a graph or a table? That seems appropriate here, right? I'm going to do it with a table because it's, well, it just feels easier to me. So I'm going to go ahead and type in what the thing I'm trying to take the limit of right here. Type that into the y equals. I'll do y1 of, well, let's do a left limit here. I don't know, real close to 0. That look good to you guys? All right. And then I'll do the right limit. Just knock that negative sign out of there. I feel pretty good with that, right? Left-hand limit is basically the same as the right-hand limit, close enough for our purposes. Right? For an approximation, this is approximately the same. So we could say then that this is approximately 0.693 times 2 to the x. Does anybody recognize the number 0.693? Mr. Kulik did when he was doing this. It's the natural log of 2. I don't know.
I recognize
I
it.
could have gotten
I
that
just
one.
wanted to see if you
That was my second choice.
So, what are we seeing here? In general, for f of x equal a to the x, the derivative is equal to the natural log of a times a to the x. Do I have to worry about this piece? I can't take the natural log of anything, can I? got to be, yep, positive. Nope, can't do 0 either. Is that okay? Yeah, because a is an exponential, right? So what values is a allowed to have? Greater than 0, not equal to 1. Right? So I can take the natural log of all those things, so I don't have any issues with that at all. The base of an exponential is not an exponential, it's a constant function now. Right? Even though 1 to the infinity is indeterminate, I think. Ugh. Those indeterminates. All right. So what about if, what's going to happen if f of x is equal to e to the x then? Well, I get that, right? What's the natural log of e? 1.
Will be going to college.
Yes. So wait, Mr. Kulik, what? The derivative of e to the x is e to the x. Yeah. That is a theorem. You can use that. So a little quick example. Suppose f of x is equal to 7e to the x minus x, and we want the first derivative and the second derivative. What's the first derivative going to be? Great. And what's the second derivative going to be? And any derivatives after the second derivative? 7e to the x. Oh, that's not so bad, Mr. Kulik. All right. So I want to take a moment, talk about one of the problems from that we had on the last multiple choices, because it lines up nicely with what we're doing right here.
Oh, yeah. Oh, this is the one where it was like negative 1/e or something.
So this was one of the multiple choice ones on the last multiple choice practice I gave you guys. So let's talk about how you would have done that using just the pieces that you had from the last chapter and prior courses. So I started by just factoring off an e to the negative 1. Since that e to the negative 1 doesn't involve the h at all, I can bring that factor outside of the limit. But this piece, if I try direct substitution, what am I getting? Indeterminate, right? 0 over 0. So what could have you done? Well, this is what Mr. Kulik supposes that you could have done. You would have started with your definition for the number e. You guys all remember that from Algebra 2? Of course you do. Okay. So what I did next was I took the natural log of both sides of this equation. And I know that the limit of a composition is equal to the composition of the limits. So I can move the limit outside and push the natural log inside. Now, do you remember your log rules from Algebra 2?
No.
Look at that log that I got in there. What can I do with that?
Use one of those rules.
Okay, Mr. Smart Guy. I can use the power property to move the exponent to the coefficient. You do remember that.
Yeah.
Now that I say it. Everybody's okay? Now we're going to start doing some change variables. Oops. So I'm going to start by rewriting or letting y equal 1 over x. Now when I do that, I won't have any more x's left in my equation, right? So the variable involved in my limit also needs to change. If I look at this, as x approaches infinity, what is y going to approach? 0. Does everybody see that? So my bound on my limit is going to change. Oops. Yep. Thank you. Okay. So there's that. Mr. Kulik's going to do another change in variable now. I'm going to say that z is going to equal the natural log of 1 plus y. And that's equivalent, using our definition of a logarithm, to e to the z equals 1 plus y, right? That that's our definition for a logarithm. And this guy, I can get the y by itself. By just, oops. Wrong way, Mr. Kulik, you dummy. By subtracting the 1 over. All right. But I'm doing another change in variable. Ugh. So as y approaches 0, what's going to happen? Oh, let's look at this one. This will be easier. So y approaches 0. What is z going to? Well, when y goes to 0, I have the natural log of 1 plus 0, right? What's the natural log of 1? 0. Everybody's okay with that? That's a calculator thing. But to think about like a to what power gives you 1? 0, right? A to the 0 is 1. That's the natural log question. Or e to what power gives you 1? All right. So, yes, exactly. Okay, so I'm going to have 1 over, and instead of y, I'm going to write e to the z minus 1. And then instead of 1 plus y, I'm going to write z. Everybody's okay with that? Multiply that stuff together. Jillian?
Can you start a thought process and redefine the why? Like, why did you choose that? You know?
Well, I'm trying to build this thing, is what I'm trying to build.
Oh, look back up there.
So I'm trying to get that to tumble out of this. So that's why I picked this Y to get rid of, like, because I wanted to get the fraction in a different place. I tried messing with this, but I needed the fraction out there, so I know. This is hard.
I don't think I can regurgitate this.
Okay.
And if you look, take a pause. Look at where we're at now, right here, and look at what we want to have. Pretty similar. What's different?
It's like upside down.
They're reciprocal, right? Or almost reciprocals. So guess what I'm going to do to both sides? Take the reciprocal. Because the reciprocal of 1 is still just 1. Now if I look at this and this, what's the only difference between the two? The negative and the name of the variable. Now the name of the variable I don't care about, right? It's just a name. But that negative sign there, at least I have to think about for a moment. What's the limit as h goes to 0 of e to the negative h? Just that piece. 1, right? You just e to the 0. If I take the limit as h approaches 0 to e to the positive h, what's that limit? The same thing. So what we have down there is good enough, right? I couldn't figure out a way to get that negative sign in there when I was doing this, but what we had down there was good enough to get it to tumble out. Notice that the stuff we did below was all doable using the stuff from chapter 1 and previous algebra 2 rules, but as tricky as the Dickens. This identity here that we just developed I've seen pop up on as being useful on the AP exam in more than one occasion. That might be one to just like make a note of. I don't think they'd ask you to come up with it yourself, but it might be something that would be useful in doing a limit problem with no calculator, is to remember this identity. So just as an aside, I'm not going to prove it again using like something else. This seemed adequate using algebra 2 techniques and like some stuff from chapter 1. Just by pushing limits around or whatever. Blake?
Could you please go back up just a little bit?
Sure.
Maybe a little bit to the right. Okay.
Teagues.
Like how on the AP test are they gonna like stop us from using our calculator?
Well, there's like 4 sections of the test,
Okay, yeah.
and there's like a break in between where it's like, okay, everybody put your calculator away, and then for the next 45 minutes or whatever you work, and then you turn that section in. Like, okay, take your calculator back out. Here's a new section. Work for 45 minutes or whatever. Turn that in. Put your calculator away. Here's the new, there's 4 sections or whatever. So that's the way, that's how they're gonna control it, because everybody does the same sections at the same time that are for the same amount of time that are calculator, no calculator. Okay. So that was section 3.1. Now that thing that we just did at the end, like that was very complicated, but for the most part, 3.1 was like here's a bunch of derivative rules to make these problems that were like whole sheeters last section turn into mental math problems, which you should be real excited about. Because, boy, that's going to make like the homework go much, much faster. So just to kind of illustrate what's going on, go over here, please. Let's just grab a couple of the homework problems and do a couple here together, right? Sounds like fun. Oops. Actually, oh boy. I don't know where this is going to pop in at. Oh, okay, good. That's a reasonable place to pop in. Whoop! All right, so let's just look at like 3 through whatever. Because these are just take the derivative problems. What's the answer to 3? Does it matter what the exponent is? It's just 0. Right?
Okay.
How about 5? What's the answer for 5? Yep. How rad is this? How about 7?
X squared.
Great. 9.
Great question.
It's going to be 2x minus 6x squared, right? Got to distribute it through, and then you can do the derivatives. This is like the fastest the homework's ever gone for me, Mr. Kulik. I know. Thank you for the derivative rules. The next one. Negative 3 over 2 t to the negative 7/4. Right? And it's fine if you want to leave that with negative exponents. No biggie. If you converted it to a radical as a fraction, that's fine too. On the multiple choice sections, if they had a problem like that, I don't know how they would write it. To be honest with you, I don't remember if they were consistently using negative exponents or not. My suspicion would be not, but who cares, right? Like, it's easy. If you can convert it one way, you can convert it the other way. 13. 60 s to the negative 6th. Or you could do it 60 over s to the 6th. That would be okay also. Is it feeling okay, guys? Was negative 3 over 2 t to the negative 7/4. Let's see. 15. What's the trick for 15? You'd have to FOIL it out first. No biggie. Yeah, so I would just think about it as negative 12s to the negative 5. So that becomes negative 12 times negative 5 is 60. And then I subtract 1. Cool. Oh, let's do 23. 23 is kind of sneaky. What do you have to do here? That's my first step, is I divide each term by its denominator. And now I can apply my power rules directly.
Wait, so why is only 3x to the negative? Why is only the negative?
Because it was 3 over the square root x.
Oh, yep, I see it.
So again, this is just Mr. Kulik doing sneaky algebra so that calculus is easy, right? So,
Can you talk about the format of 21? Like,
yeah, does the a, b, and c are constants, so it just becomes like 3au squared 2bu plus c, because we're the variable in question is u.
that's fine, but like, where did they come up with this? It just seems like
The AP particularly likes these kinds of questions where like there's constants rattling around in there, so you can't just like type it into your calculator to do stuff. So I see that happen rather frequently, especially in the no multiple or the no calculator sections. They'll do that just because, or they even put it in the calculator section, so your calculator is just not very helpful to you. Which we've seen on, I think, on the multiple choice practices, like, oh, this is a calculator active one. It's like, what would I use my calculator for on this? I don't know. In the free response questions, the calculator active, you absolutely want to have your calculator. That is enormously helpful, and it will save you a tremendous amount of time. But on the multiple choice, it seems like there's a lot of questions that are just like, I wouldn't have used my calculator to do this anyways. But look at that. We just did like, I don't know, like 10 problems in like a couple of minutes. That's pretty righteous. Paulie, what's up? Yeah, man. That's his, yeah, Jack. 9?
Yeah.
Distributed.
Oh, you should. Okay.
Yep. And then just did my rules after.
Okay, yeah.
Right? Just made it to a polynomial. I gotta get into that polynomial form. Once I do that,
Okay.
if I just have terms added and subtracted, there's no problem. Problem is I can't do multiplication of two things yet. Can't do division of two things yet. And I can't do like one function inside of another function yet.
Okay.
We'll fix all of those things in the next couple
2x
sections.
minus 6x squared. Okay.
Yes, Teagues.
It's probably like kind of in the future, but I like when I look up like an algebra solving question, and they would use like L'Hopital's rule or something.
Yeah, that's a thing. We'll talk about that here relatively soon.
What's it called?
So what he's talking about is there's, yeah. It says that the limit as x approaches a of f of x is equal to the limit as x approaches a of f prime of x.
Oh, so you can just say that.
So sometimes it'll be easier, like if I just take the derivative of this thing, then the limit's easy. Can get out from the indeterminate form.
Yeah. That's smart. Yeah.
So that's something that'll be coming. That's coming. But that's just another way to avoid those indeterminates without having, like maybe the algebra is just not feasible.
Yeah.
Or it's like,
It's not something that you can really.
or you can't, or maybe you can't even come up with. Just like the squeeze theorem is another thing you can use if the algebra is just like, I don't even know what to do algebra-wise here. You can try to sandwich it between, you know.
Tegan, are you going to do the reference?